Phopon. I also go by NCI or not NCI. If you have checked out my blog, cough cough, not NCI.rocks. Nowadays, I'm mostly a bug bounty hunter, getting into AppSec because Martian's forcing me to. But I kind of got my start in hacking as a whole through video game hacking. That's how I learned assembly and reverse engineering, which got me to doing malware analysis. That's what we're doing today. We're going to be looking at a sample that I essentially used as my first real test of skill. It is a sample of the NotPetYa malware, if you remember that. I don't remember the exact year, but they targeted pretty large shipping companies over in Europe and took them down for a while, which is always a ton of fun. So for we are going to be using IDA. Again, you can use the free version, it's fine. You will unfortunately be stuck in graph view and code or text view. If you have the pro version, you can, wrong key button, sorry. There. You can press F5 on your keyboard and it'll turn it into pseudocode, especially when analyzing complex malware. Despite this, there are still downfalls to this pseudocode creation, as you might see in newer variants of malware that have specific technologies implemented that will, for example, break the stack tracing of certain functions, which forces you to step through assembly yourself. That won't really be an issue in this sample, but it is something you will have to watch out for if you are looking at something more recent. So the plan for this is that I'm kind of just going through this file as I would if I were first looking at it. That's why I have a completely unanalyzed copy of the binary here, and I have another copy of IDA database up in another window, which we will be going back and forth in between. Would look like in the end being analyzed. So start looking at any type of malware. There are some default windows that come up in IDA. For me, the most important ones are always imports and exports. Your DLL main or your DLL entry point, your win main, generally main function, and any other functions that are designated as exports. In the case of this, since it's a DLL, there's a custom function that is exported, which is actually the main malicious function, which we will look at in a little bit. Generally speaking, our exports don't really have too much. So let's look at our imports. This is where things get a lot more interesting. So if you've looked at malware, especially ransomware, for a while at least, you will see a lot of common themes in the imports that they use. API lets you do cryptographic operations. So for example, crypt gen random, crypt acquire context, all of these things are in the creation of the encryption key that the ransomware uses for that machine. Other things to look out for in basic privilege escalation scenarios, you will often see things like duplicate token X, set token information, get token information, especially adjust token privileges. This can basically steal the privilege token from another process, which they will eventually use for executing lateral movement once they have privileges on the host machine. Interesting things are the DHCP API things, which we will get into a little bit, but it is a lot of networking stuff that isn't necessarily at the core of what is important. Other things in general for malware to watch out for, virtual protect, load library, virtual alloc. If you have watched any sort of unpacking videos, some sort of packer evolved, and you're trying to manually step through the unpacking, in like x64 DBG or whatever it is, you're always going to your memory region that gets set to read write X. So those are obviously things to look out for, or any of its kind of similar function calls are not necessarily always malicious, but obviously things to look out for. You're creating a file. These can also be used to access or create pipes in certain ways. From game hacking experience, seeing create tool help 32 snapshot is a clear indicator of someone trying to enumerate the running handles on a system. That is just kind of prior experience that I had, and it is by far the most common way to create a sort of loop where you create a snapshot of all handles and then parse through them and find the executables that those handles belong to. That is actually pretty important in this malware specifically because if you quickly reference the white paper, there are specific antivirus vendor checks that basically Bitmask for certain operations within the malware, and the way that they find out if these specific antiviruses are running is based off of enumerating the running handles, which is what the create tool help 32 snapshot is useful for. So since I mentioned it already, the main malicious function here is what is going to be called we know this because exports are named because they have to be accessed in some way by the code that is trying to import it. It can be accessed explicitly by what is called its ordinal, which is the number right here. So if, say, the loader of this malware via the ordinal, we wouldn't ever know the name of the actual function. But, you know, we know it's purposely one because they did it that way. Now, as we can see, we go into graph view, it becomes even more clear. This is a ginormous function, and there are a lot of calls in here to different subroutines. So, something nice that we can do here now, because we're in IDA Pro, is simply click F5. Now, this does look very intimidating because all you see is sub, blah, 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 bunch of random numbers. But this is where kind of just having an eye for things helps. So if we go back to our imports, we kind of have an idea of what could be used maliciously. We are looking for what is calling load library W. You can press or double click it, highlight the name, press X to find the cross references, so where it is called, and we can then just go look at this. Okay, now we're in a completely new subroutine that we haven't looked at before. We press F5 again to decompile it, and okay, this looks a lot easier to approach than what we had previously. So, load library, sorry. Load library in general is going to be followed by a get proc address, because load library loads a Windows DLL essentially, and then from that Windows DLL handle we can pass that into get proc address and get the function address of that. So what the checks here are doing is checking if we get a valid address back. So this would, for example, what I would name like P for pointer, and then get extended TCP table. So now this call down here makes a lot more sense because it's not just, you know, a v3. So here we're actually calling the function via its pointer. So code, this would be a prototype function, if you know what that is. So now that we know the actual function call, we've got parameters here. But we don't really know what these parameters mean. This is where Google is going to be your biggest friend. About 60% of my time reversing malware.
Fopon, did we switch screens there?
Not yet, no.
Okay.
I'll switch screens.
Yep.
But yeah, roughly 60% of my time is going to be spent on Google looking through either MSDN documentation or websites that document undocumented Windows API functions. Once you get into the nitty-gritty of it, especially if you start reversing, Windows internals themselves, you're going to be spending hours on there. So really, getting good at reversing is getting good at knowing where to look for the information. So if we quickly take browse here to get extended TCP table, I think that was, yep. Okay, we get some documentation from Microsoft. Lovely. Okay, now we know the actual parameters. So the first one is going to be a pointer. Since we have pvoid, be a pointer to our TCP table, the size of it, ordering, and really not that important stuff. But now, most importantly, we know that a pointer to the table and a pointer to the size are going to be the first two parameters. So we now know that this is p table, and this is p table size. We can name it like this. The weight doesn't really matter. Just in these kinds of contexts, I personally prefer prepending p if I know it's a pointer specifically. But the rest of it is really completely up to you. It doesn't really matter. So we see now here that this is our table. Our table is allocated onto the heap because we need to allocate space for it. Then we're looping through the table. Oh, I didn't switch screens there. That's my bad. But basically, the issue we run into is that we are looping across this TCP table, which means that it's a structure. In the code, we don't really know what the structure actually is, or is even, because all we know here is that we have a member access at offset 18. So until you have it converted to a structure, all of your structures are essentially going to look like this. You're going to have a dereferencing as your sort of cast, then your actual object, and then the offset of where that table member is. In certain scenarios, documented structures. In other scenarios, they could be completely custom structures written by the malware author. This is where a lot of the depth of understanding a malware sample comes into play. So for now, that's a rabbit hole we're going to skip because there's another function call in here. So my kind of thinking is, okay, we've done something with parsing the TCP table. Let's see what we're actually doing with that. The parameter passed to it for now is A1, which is the original calling function. So all of your parameters are going to be named in an A number format, while all of your local variables are going to be named in a B format. So we go into here. Now this is where things get really interesting. So as I mentioned before, it only showed us that one parameter was being passed. But as it turns out, once IDA actually fully analyzes the function at the call stack, there are 3 that are passed. Part of the difficulty in analyzing any kind of binary in any sort of decompiler and disassembler is that it analyzes as you go in. So if I go in here, we have a bunch of weird stuff, which I don't expect anyone off the top, because going down this rabbit hole was probably the biggest issue I had during the entire analysis of it. But as you see, the more we step into these functions, the more it turns out that our original parameter typing and parameter count is wrong. So the kind of rule of thumb is, don't do things, or like, for example, create structures too early before you know what else is using it, because what you see at that moment could just be a faulty analysis. And even after you jump into it and decompile it, it could still be a faulty analysis. That's the unfortunate downfall of all modern technology. It simply cannot track every single possibility. But that philosophical speech, what we see here is that we kind of do stuff with the TCP table. Okay, so instead of leaving this function completely unnamed and not really knowing if we touched it or not, we can call this TCP table stuff. When I don't necessarily know the full purpose of a function, I will usually do underscore and append something or stuff or unfinished or some sort of indicator that is unique, so that I know that I still have to go back to them afterwards, but at least have a basic idea of what the function does. So we can click X again to find the cross references and see that it's being called here, TCP table stuff. Okay, now IDA, because it is a lovely, great tool that you should never pay for because it's money, but is very useful, can do things as already putting in enum types. So a lot of the things when you will see like function calls that use bitmasks, like for example, a virtual alloc or a virtual protect. In certain cases where those bitmasks aren't too difficult, IDA can actually pre-generate the kernel database of, Windows API knowledge, because it imports structures based off of the libraries in the import section. So that's kind of how you know some stuff about these functions already when you go into pseudocode in IDA, which is very, very useful. So what we see here is more stuff with thread parameters. That is because this is a multi-threaded application. Going to be a lot of just random junk code dealing with threading and mutexes. But what I hope stood out to everyone is that we have 2 representations of localhost, 127.0.0.1 and the regular localhost. And again, I kind of like to point out the things that IDA does a bit weird, because, for example, in the first function call, it just drops the parameter directly in, but it also allocates a local variable for it, which this is simply the compiler doing optimizations, and IDA doesn't really de-optimize code because that could potentially break the entire logic of it. So you will get weird looking stuff like this where you'll have duplicate names, duplicate parameters, stuff like that. If that comes into play, like for example, if I were to name this LP parameter, this would work fine because it is still this local variable. First, this is a, it can differentiate those. But now, if I were to, for whatever reason, rename this to LP parameter as well, it would tell me that there's already one present with that name that is a local variable, and you can just say yes and it automatically append a suffix to it. Neat little thing if you don't want to write out new names yourself. But what we're going to do first is what this function does, because it gets called 3 times, so it's obviously quite important. That really didn't help us, did it? And we're back at this section where we don't really know what's going on. That's okay for now. Because what can we do? Localhost stuff. And this kind of thing is perfectly fine. You don't have to, oh god, you don't have to fully function before you move on from it. That's just not really feasible in this kind of scenario. So what we can do now is just go up and xref even further, and now we notice, oh, we're in perf C. Okay, so we've actually made progress now because we know that one of the threads that gets created relatively early on is to do some of our localhost and TCP table stuff, which we didn't know before. Before it was just another subroutine that we knew nothing about. So this is kind of the process that we can continue on with. So we know that create thread probably starts interesting routines. So let's look at other implementations of create thread. The function call is always going to be here, and it's also going to be highlighted in whatever color your color scheme has it set to. So go into this random one. Okay. So quick glance over, we have loops, we have more threads being created, function calls, there's stuff happening to the heap. Okay. What I notice here from the start of the function is these mentions or these references to this random D word, which is a global variable. So we can look for cross-references to this to see where it gets written to. So we can look in the type here. All of these are R, but we have one right. Doesn't this look quite interesting? So once again, if you have the white paper up, there is a section of code that looks very, very similar to this, because it is this code section. But for those of you who have, like Windows pen testing experience, you will know that these things are used for privilege escalation. So what is this function call? We can guess that it is, probably getter set privilege value, but it's actually a little more, a little more sophisticated than that. But as you can see here, a lot of the stuff, like a lot of the structure in the token privileges structure, were pre-filled. I did nothing to do this. That is, again, one of the lovely benefits of using IDA Pro. You have to do less work, you know more. So what we can broadly call this is, there's kind of 2 ways to go about it. So one way you can do it is, the most important call here is adjust token privileges, right? Because you're looking up the privilege value, you're then adjusting your own privilege token to that of the new state. Okay, so since that's basically what it's doing, we could technically just call it wrap adjust privileges. So when we go back, we have a better idea of what the full purpose of the function is, rather than giving it some arbitrary novel name, because the rest of the function calls are really just, wrapping around it so that it works nicely within the Windows API. If you make these kinds of changes, like that are large because you kind of made a breakthrough in understanding what a code section is, be sure to save it manually with the save button, because sometimes when you click to return to previous position, if you don't, these things can get reset. It's just a weird bug, again, modern technology. But as we see here, we have a call to get tick count, which is saved to a global variable, so we can rename this global variable. current tick count. This here, this was our original variable that we were looking for, is being set to v0. v0 is this. Okay, so we are using a bitmask here. We know it's a bitmask because we're using bitwise operations here to try and set privileges. So we can name this privilege bitmask. Nice, we know a lot more now. Save that. Now, anywhere this is red, example here, we now know what this actual bitwise operation is and what it's looking for. So as we continue to progress internally into these small spaces that we go digging into, once we come out of them, we will actually have a good idea of the reasoning of what is all going on. And that is kind of the general approach that analyzing any sort of piece of malware is. Like, I guess it would be like a recursive method of analyzing it. So I find one entry point and I will dig to there up to a point where I no longer feel like it is worth digging for that moment. Go back out to where I started, see what makes more sense or where there's a hint, and then keep digging there. And that kind of process is kind of what you have to do with analyzing a complex piece of malware. Once you get more experience, there are a lot of things that will stand out from basic indicators. As I mentioned earlier, for example, from the imports, there are ones that immediately stand out to me as being indicators of compromise or indicators of malware specifically. So that all comes from experience. You just have to read and look at malware and understand what it does over and over again until those kinds of things become second nature. With the earlier mention of optimizations, there's a lot of stuff that the compiler can do to make your life as an analyst so much harder. And I don't enjoy my life being hard. So I do things to make it easier. With that all out of the way, you can probably see me kind of hovering around this here, which for blue teamers, I would assume you are probably familiar with. When I first saw this, I had no clue what was going on. So what I did is I took this last piece because I feel like delete journal is probably something destructive. I just copied that. Let me switch my screen to Chrome. I copied that over to Chrome. More Microsoft documentation. As I mentioned, you're going to be learning from Microsoft a lot. And the more you're here, the more you're going to realize that their documentation sucks. But we can look here. We can Control F for delete journal. Okay, so actually, does anyone here that knows want to explain what the USN Change Journal is used for? No? Okay, fair enough. From what I remember, the like shadow copies of the file system, I think. But we can obviously also just look it up. So yeah, it is a record of changes in the NTFS. So kind of having the precursor of understanding that this is ransomware, deleting files isn't good, or deleting indicators of file changes obviously isn't good. So if you're a blue teamer, the specific string that is embedded in the malware, let me change back. This specific string here, as this is a, a full ASCII string, could be put into like a YAR rule or whatever other enterprise stuff you use. I don't know, but you can put that stuff in, detect it. That's kind of the usefulness of kind of just having an eye on what is going on, because you can provide these indicators, which are, I feel like, relatively unique. I don't really see a legitimate way that this specifically would be used. So from there, you already have an indicator that you can then give to your supervisor, whatever you want to do with it. Cool. What we do have to realize, though, is that this is quite far at the end of the function, if you see the scroll bar. And right below it, we have a call to NTEraseHard Error, and then initiate system shutdown. Basically, NTEraseHard Error can be used to force shut down your computer by creating a specific. Again, we have this kind of scheme of get module handle, and then get proc address, and then us calling the function by its address pointer. So p NTEraseHard Error. That's fun. Weird number here. That's because IDA by default has numbers in binary, or in like regular numbers instead of hex. If we change, we have a much better understanding of what the code could be. So let's look at NTEraseHard Error, because I don't think that's necessarily a function that most people even knew existed. Now, we kind of see that a lovely link to learn.microsoft.com. That's because we are in the realm of undocumented functions. As you can also see here, we have a lovely GitHub repository that says quick bsod. So I think you can kind of guess where this goes. But pnvoke is generally a great website for this, because they give you lovely signatures, blah blah blah, and some sample code. So if we remember earlier, in the privilege token checks, since this is being brought up again, this SE shutdown privilege, otherwise it will fail. So if we check back into our code, there is a check to make sure that we do have shutdown privileges. Now that we're down here at NTEraseHard Error, makes sense. So we're checking Bitmask, ending it with 1, go back to the right location. Look at that. It's for SE shutdown privilege. So now we actually have a really good understanding of what this code path is doing overall. So what you can do here is, for example, you can add comments onto these lines by pressing your /. So what we can enter here is privilege check for, and we can copy the SE shutdown privilege over from token privilege check, call NTEraseHard Error. And now we have a comment here that we can refer back to sometime later on when we're going through it. Oh, here's what I was mentioning. NTEraseHard Error. Now it's back to V11. I forgot to click save manually beforehand. Again, software. But broadly, we kind of now understand why in the beginning we are even checking for SE shutdown privilege. Because up until now, it was just another token privilege check that seemed relatively arbitrary. But don't know if it has it loaded, but if you have these kind of, hexadecimal values that are obviously, a specific code, you can press M, okay, and it'll generally come up with this. You can search for standard enums, yes. In my personal opinion, I wouldn't apply this enum value. I would just make a comment on the line saying value for BSOD shutdown. That's what I would personally do. Obviously, there's more digging that you can do to find the action. If you go to the enums tab, there's instructions here. You can create your own. So you can create your own symbolic constants if you're, again, analyzing custom malware that has custom structures, that kind of stuff. But for now, comments actually do a really good job of doing what we need them to do. So kind of know what it's trying to do broadly in terms of at the end. So it is going to delete all the changes from the file system that were made. It is then going to check if it has elevated privileges for SE shutdown. It calls this NTEraseHard Error for a BSOD. If not, it calls a slightly more documented function, initiate system shutdown. If that doesn't work, specific operating systems, they call exit windows. This is kind of a funny way to think about the amount of work that even malware authors have to do to keep up with the amount of old technology in the industry. So yeah, not saying keep old systems. Don't do that. But even the black hats have to work around industrial negligence. So now that we kind of have figured out this bottom part, we can scroll up because you have more access to this privilege bitmask, which means there's interesting things. So why not look at this? Oh, well then, this doesn't look like a usual string of letters you would see. So this is definitely something to be looking out for. Like if you're first looking at this, you're like, what am I looking at? So the other things here is calls to get logical drive and get drive type. For now, we're not necessarily going to focus on that, but again, with the context of this being ransomware, it makes sense that, there's stuff happening with your drives. So drive stuff. Perfect. We also have a call to create thread here to the start address. Again, we dug a bit deeper, and now we are in the actual cryptography aspect of what is happening in the NotPetYa malware. So earlier, the crypt functions are generally indicative of there being some sort of cryptography going on. So we have more functions at the bottom. This top stuff doesn't necessarily matter yet. You could convert these, for example, see if there's a specific error code that makes sense. We can apply that. Do the same here, see if there's anything else. So these are basically correct because crypt acquire context is generally dealing with specific key sets because you're passing a specific set that you want to get the context for. In the end, it just makes it look a tad bit nicer. But function calls. Oh, crypt gen key. Okay. This is now where, if you're looking at okay. We're now in, generating the encryption key for the actual data on the drive. So we see here, we're generating the key that gets returned here, so we can rename this crypt key. And the function name we can do generate encryption key. I'm not necessarily keeping naming schemes like the whole way through, but it doesn't really matter. These things here analyzed further to make the code structure look nicer, so you have like structure member access and that kind of stuff. But broadly speaking, it doesn't really matter to the understanding of what's going on here. So save that. Now we know that we are generating the encryption key. What are these other functions? Oh, okay. We have a list of file extensions. And from a little bit of looking at the code and of just broad knowledge of how C++ works, you have path combine W with find first file. Those are just indicators of you are looping through a folder of a file system. So we can look down here to see what's actually happening in the loop. So all it does is it finds the file name, prints it out, and then compares if the extensions are in this loop. So there are some interesting ones that specifically show that this would be targeted at enterprise systems. So for example, with the encryption of VBox, VMDK files, those kinds of things to lock up virtual machines, destruction of important information through code with .py, .pyc, .php, those kinds of things. So the kind of most can be determined partially, at least, from looking at what specific files they are targeting. And again, this kind of a string in this order can also be used in another Yarrow rule or something like that, since the way they are set up is relatively unique. But we see here that we've also got a reference to C windows. Then, here. Oh, yeah, we're recursing. Got it. So yeah, down here, if we are like in a root directory, we are just going to recurse back and keep going through the file. So this is going to be the file encrypt loop. And kind of the most important function here is bad boy down here because it's being called if that extension exists. The big thing here is calling Crypt Encrypt after getting mapped to a file. So my assumption here is that you can kind of understand the purpose of Crypt Encrypt. If you hover over a Windows standard library call, if you're lucky, see the parameters and parameter types. So we have the key, the hash, whether it's final, flags, a pointer to the data length, and the buffer length. If you haven't necessarily dealt with like raw file system interaction, you might not have interacted with create file mapping or those kinds of things. But again, what's really important here is the call to Crypt Encrypt. So Crypt Encrypt, and realistically, we can just call this wrap. So we have our file name here. It does some stuff with the Windows API. So this access, is it in here? No, unfortunately not. Okay, so with create file specifically, it makes it a bit easier if you can get an enum mapping into here, because there are specific privileges for file access. That's that, access, each template. So yeah, what we can also do, because MSDN does have documentation on this, is we can look at what MSDN says about it. Because oftentimes the enums are actually still on their page, just about 2 to 3 links in, which It's kind of painful. But create file W, and here, so in the hex value, that is our desired access value, which is just, another Bitmask flag. They're kind enough these options here. So if we go to access mask, we can get a list of the values that can be given. So, generic read, generic write. Oh, this wasn't here before. Yeah, if the documentation is updated enough, you can get actual hex values. If not, you're just going to have to find another web page that has them if you want to manually create that enum in there. So essentially, we're creating a file or creating a handle to the file with the given file name that we have passed as a parameter, which if we go back, it's already shown us as the file name parameter, which IDA thankfully deduced for us based off of the Windows function calls themselves. So we do that. Now, what we can do here is we could destruct, right click, convert to struct. You can search here for certain structure types if they are included in your IDB. So if we look at the parameter typing, it should be the H key, which is an H-crypt key. So we can create a new structure. We know IDA is basically just pre-filling information in bite-sized gaps for stuff that it doesn't specifically know about yet, which makes sense because the most important thing is the sizing of the struct, not necessarily the types within it. So if we just click OK on this, our code gets a lot nicer. Now we have actual, member access code that we're looking at. So since we know that this is supposed to be a handle to a key, rename this to H key. Save that. And now we actually have a structure here that is now pointer. And once we go back to what is calling this function, first encrypt loop, we now know that A3, which is parameter passed to the file encryption loop, is also that structure. So I was pinged. Oh, switch screen, sorry. Yeah. Let me go back through those steps again. So yeah, we're here down at the bottom at Crypt Encrypt. We know that this needs to be H key, like A2 plus 20 has to be H key for Crypt Encrypt to make sense. So what we can do is convert this to a structure. We look here. These are all going to be basic Windows structure types. I don't know if that window, no, that window's not going. Never mind. Okay. Thanks, Discord. We're simply going to type. This again will then refill from what IDA knows within this function. We click OK. It looks a lot nicer. We can rename this to the member of H key because we know that needs to be our parameter for Crypt Encrypt. We look back on it. We now know that A2 is actually just a pointer to the structure. Figure out what more there is to the structure. We look at where it was called again because our parameter is going to be updated. Now we know that A3, the third parameter in the file encrypt loop function call, is actually the structure as well. What we also figure out from up here is that it's actually larger than the size that we previously thought in the function. So now we can convert A3 up here, convert to, and since we created it, we can now just apply it. Now, it's looking weird up here because it's obviously a larger size than it was before. This is where, hold on. Okay, so if you want to edit your structure manually, you can right-click, jump to local type, to the local type screen. Your structure is down here. You can click edit. We know that we have another value afterwards. So this specific screen is not showing, is it? No, it's not. There. Okay, so this is what it looks like when you are editing a structure. This was already pre-filled as we saw, but our sizing isn't correct. So what if we put another keyword here and just make it unknown 1? Click OK. And that synchronized to IDB. That's fine. Oh, screen share fully stopped. My bad. So we write synchronized to IDB. It's going to complain. That's fine. We go to our local types. We reset the pointer type. And now we reapply the new structure. Okay. We're still in gap 0. So this kind of process, obviously, you properly read offset was, and you change it that way. But this is kind of how you have to retroactively edit your structures to make things make sense. You know, because IDA only knows as much as is kind of currently on the screen. So even though Crypt Encrypt here gets called by this function that has more to the structure than we first knew, IDA can't necessarily handle that. So what it does is just creates them, but you're responsible for continuing to edit them to be up to date with the actual size the more you figure out. So when dealing with these structures, that's why I kind of kept it until now. You can run hard work because you're manually mapping out, custom structures, address space, without having any documentation. This was a kind of thing I did a while back as kind of a practice run for myself. Is I took a Logitech driver because they obviously use custom structures to pass around data with the IOCTLs and try to reverse those. Let me tell you, but you kind of have to go through pain when you're trying to analyze anything on an assembly level. It's the inevitable truth. So with that all being said, we know now that A3, is a structure. So we can kind of just call it data struct because it has some form of data in it. Now, file encrypt loop gets called at the start address. Now is where things get really interesting because our thread parameter is actually also the struct, which before we really had no clue about the thread parameter even being a structure. Now we know that it is a structure that is probably going to hold part of the encryption key. So now we can go back into generate encryption key, and these A1 pluses make a lot of sense now. We can convert this to struct. And okay with this, A1 H key. So yeah, that's gap 08. that is going to be the H provider. Okay, so as you see here, we're still back in that kind of recursive structuring. So because the size that we set for our structure is smaller than the actual size of it, we're going to need objects. That's why in some examples you saw like A1 and like in parentheses an array access of like member 1. But that's kind of what you have to go through. So here we see we're 8 bytes into gap 0. If we go back to our local types, we edit this, we're 8 0. So into, wait, sorry, math. Keyword H prof. I think this should be it. Reset pointer type. Oh, it was one off. Reset that. Sorry, my mental hex math isn't on point right now, but you know, that's how it goes sometimes. I'm praying that I did this correctly now. Yes, lovely. Oh, well, I messed that up. Regardless, the point is that you kind of just have to continually re-edit your structures if you are going in the way that makes the decompiled code look nicer. Again, this is optional, but if you have something that, you know, has over 100 function calls, it can be useful. But with all that being said, we're now stuck on the idea that our LP thread parameter is an entire structure. Okay, so once again, what calls start address, and from the create thread function call, the address of the function that's being used in the thread and the LP parameter that is being passed are right next to each other. So in this case, it is going to be the result. The result is a large array, rather a structure. But now we also see that, for example, are the current root path name, as well as this entire blob of stuff. So once again, we have a much better idea of overall the path this malware is taking. So this is kind of what you continue to do through every single step of the malware. So once again, we go back here, we're back into like the main thing of what's going on. And this process is what I repeated over and over again until I was at a point we're going to be switching over to here, do that, change windows, this one. All right, can you see with everything nicely named now? I hope so. Yes, okay. So the difference between, you know, when I started out and was doing this, you know, for an hour off rip versus at the end when I had spent multiple weeks reading through the code, it makes a ton of sense. The first thing we're going to do once this is loaded So because this is a DLL, it essentially means that there's already another malicious process running that is going to use this to further escalate its privileges. That's why the first thing we have done in the perf.c export is actually setting our privilege values to see if we can token privilege escalate. Then next, this function here actually turns loading a DLL, loads DLL, blah, blah, blah. Basically, the important stuff, it allocates memory for the allocated DLL. That's that. WSA startup is mentioned in the write-up as well. Here, the TCP table makes a comeback. I never fully explored what all the TCP table does, but it turns out levels are actually just wrappers around initialized critical section, which, as I mentioned, because they do a lot of multi-threading. This, hold on, debug info. There was a really weird thing that I noticed when it came to the critical sections, is that the debug info would wrote out. So I asked people who were much smarter than me at that time. They were like, we've never seen this before. So maybe it's just some sort of weird optimizing that the compiler did. I don't know, but they did delete debug info from their critical sections. I'm still stumped to this day on that, but we can see here, just basically right after the start, we're already going to be checking if there is an infection on the PC present, because if there is a specific file already present on the computer, it will actually not go through with the infection, because if this path exists, it exits the process completely. Yes, in here. Oh well. But yeah, this was basically one of the easiest NotPetYa kill switches, is by just having this file present in this specific path. Otherwise, create a file. And it's delete on close because the malware is technically running constantly on the PC. So once the malware closes, it will close. After we get into the first really destructive part of what this ransomware does. So if I remember correctly, this creates a handle to the disk drive itself, rather than just like the disk folder. All it does is allocate empty space, sets the file pointer to empty space, writes the file, deletes it, closes handle. Basically does that for the whole thing. So it's just empty space now. Then we get to trash MBR, and we once again have this indicator of create file A with this here. Again, blue teamers probably have seen this before, but I'm going to cover it nonetheless. So we can Google that, hopping over to the other screen. Oh, thanks for making it a file path, Chrome. I love modern technology. Okay, thank you. As we see here from our lovely, extremely smart friends over at Stack Overflow, it is what contains the master boot record. Again, destroying the master boot record, probably going to mess up your computer pretty badly. So them doing that doesn't really, surprise me. But this was also kind of a new thing to the NotPetYa malware at that time, because they do a custom bootloader. So a big thing about NotPetYa was like when you turned on the computer, there was like that, I think it was like red message that gets written out or whatever. That's basically caused by this here specifically. It's trashing the MBR, and it then overwrites it. You know, your C drive and your MBR is basically completely ruined. At this point, since we already set the privilege values, we can create scheduled tasks. So a lot of the stuff is basically just scheduling a shutdown time. We're running it as system, check the version info of the OS, because again, Windows backwards compatibility. So we check the token available here. For the value there, if we quickly go back to AppSec privilege values, is SETCB privilege, or yeah, sorry, SETCB privilege. So if we have that, we can run as system, and it's going to create a schedule at the start time to run shutdown.exe. And then it has this lovely little wrapper function call, which creates a command line hidden from view, because in create process W, we're passing the create note window flag. If we look into the startup inf, does that get passed here anywhere? No, but basically, we're just finding the location of cmd.exe based off of the comspec environment variables, so they don't have to fully hardcode a path in there. All fine and dandy, but it's a nice, neat little way that they're executing, command lines without it really popping up on the screen. So all of that, blah, 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 create scheduled task system. And these kinds of just step-by-step functions are kind of the most difficult, because until you figure out what is going on around them, their internals don't necessarily make contextual sense. So, for example, here, wait, this was, yeah, so a part of their deployable was actually loading a resource from binary. And this would then be used as part of the name pipe communication system for like interaction between the two processes, as well as inter-thread action. Because once again, the most difficult part about this is dealing with the fact that it's multi-threaded, because malware authors. But there are like tricks that they partake in to make the malware itself a lot more destructive than your quote-unquote normal ransomware, which is, I feel like personally, why you did see the impact that you did. And some things that came up afterwards, I think we can get there from looking at the imports. So we obviously talked a lot about the network stuff that was going on earlier, but we didn't really look at it. So, for example, we can just look at get adapters info. As you can see here in the xrefs, I've already had some references to that I looked through. We can F5 into this, and this is where we start kind of network nitty-gritties of it. This is where I personally didn't put too much time into researching it, because my networking knowledge is quite limited. But what the broad takeaway is that it firstly scans all of the available computers from your computer on the network. So that's very obviously something that is going to be present if you're targeting enterprise environments. If you were lucky to catch it over here, or if you remembered NotPetYa, it actually used the eternal blue double pulsar vuln to do lateral movement through enterprise networks via SMB. Originally, I was looking at this and I had no clue what was going on, but this is just actually the compiled version in this sense of the double pulsar shellcode. But if we look where this gets called from, wow, we have a lot of calls to that. We go here, and we start to get a little bit better information. A lot of these things are wrapped functions, once again, because of optimizations and whatnot. But one thing we're seeing a lot of is open socket and connect, which comes after this random function, which is a socket once it finds a host that it can potentially connect to. And as you can see here, taking the approach of simply double clicking your subroutines eventually does go a little haywire. But one thing that I would personally use nowadays, if I were to go along with analyzing at that time, relatively novel malware, is get a better idea of current exploit shellcode. Because if I had any clue that, this entire block here, which, if you think about it, is pretty recognizable, especially XORing with the 0xCC, which I'm pretty sure is part of the interpreter encryption. Someone can gladly fact check me on that, but I think that's what the 0xCC XOR was. But yeah, kind of just having a better understanding of current exploit shellcode would have made this entire section a lot easier to understand. A lot of other file names that you will have seen in this section will have unknown or UNK just added. So for example here, as I was talking about, when it just did stuff with thread critical, I tried to understand it, but as you see, stuff just gets left at UNK for unknown. That all being said, if we look at the actual main perf exported function, that doesn't really affect us at all. Because anything aside from down here with the one thread thing, but the actual malicious actions that are taken by the malware are essentially completely understood. So reversing well isn't necessarily dependent on how many of these subroutine names you can change into something that's understandable. Because this to me, yeah, we have some heap Alex, some freeing of heap, we're copying memory, we have an unnamed again. All of this in the end is just residual information that are kind of rabbit holes that you're going to get stuck in. Same thing when I dove into the entire socket wrap select and receive, because, why are we turning this? Those are rabbit holes you will always find yourself in. But the biggest thing is finding yourself back out of them. Find one function that is kind of the start of everything, which is why these exports are so important. Because realistically, everything important that happens, you should be able to step back through your function calls upwards, and you should reach back to that initial perf C that you started at. As long as you can keep yourself on that kind of a track, you are going to become a better reverse engineer in general. And yeah, that's kind of really all I had planned in talking about. I obviously could go over more of the sections and reversing them myself, but this IDB here is published. I'll drop a link to it afterwards as well. So if you want through the annotated code for example, here in infect MBR, since this is how one of these strings also comes up. There are certain Bitcoin addresses that are in this code, which you can find if you just kind of look through the strings. Here we have strings that are references to Windows API calls. If you have something like a piece of malware, one thing that a lot of malware does, dynamically allocating imports. So you won't really have anything in your imports section aside from specifically get module handle and get proc address, because those two will always be necessary in order to get any sort of Windows API function calls. They might not always be in this tab, but if they aren't, they are going to be strings. That being said, let's see. That was that. A lot of this is kind of just junk because strings are just hex data, and the more you consider random hex data to potentially be a string, the more junk you're going to have. So if you want to, for example, have less junk, click setup. This window won't show, but you can, for example, set limits for what the minimum string length is, what string types are allowed, that kind of stuff. But oh yeah, here. So down here, we actually have part of the like ransom note. So please reboot your computer. We can actually use these strings as cross references. Sorry, to find interesting parts of the malware itself. So repairing file system, we can no cross-refs to that, no cross-refs to that, no cross-refs to that, none to that. And this is where you run into the small issue with this specifically is we should have a, yes, so there is a string called readme.txt. This one have an xref to it. As you can imagine, the file name is create readme. But we actually have the file now where we're creating the readme after encryption, as well as the specific Bitcoin wallet address, as well as a contact email. So from a forensic investigator, you've got two really huge indicators now that you can track this TA by. You have most likely compromised or fake email, but you have a Bitcoin wallet and cryptocurrency. All of it can be tracked. A few weeks back, I did actually go and check through the transactions from this Bitcoin wallet, and either I ran into like foundational base of one of the largest coin mixers on the darknet, or their operation's just a lot bigger than anyone ever thought. I don't know. But I clicked through Bitcoin accounts for about 45 minutes until I gave up just from this one Bitcoin address. So if that is something that interests you, please have at it.